fields, nonlinear spectroscopy, manipulating on the path.
This gives you a pulse of
we know a lot about control and dissipation and so forth, and I would like to give like a different twist to the whole issue, namely that when you have, if you treat the electromagnetic field quantum mechanically and you are driving a system, you have a problem of two coupled quantum systems. And then you can describe what's happening in some form that is similar to the way you describe the driving by external field, except that when the external field is a classical field, you can describe everything by response functions. And the response functions are causal. The field is causing the effect, and whether you do linear or nonlinear, everything is given by response functions. However, when you have the two interacting systems, you get a more general type of quantities that are related also to spontaneous fluctuations in the two systems. So spontaneous fluctuations are not causal. They occur at random and you have no control over them. So basically, the description of the problem is in terms of correlated coupled response and spontaneous fluctuations. And it turns out that there is a lot of insight that can be gained by looking at it either in Hilbert space or in UV space. In fact, even though I spend most of my life in UV space, there are certain aspects of it that are better understood in Hilbert space. So I would like to give you some, to show you some results that we did recently with response to quantum field with entangled photons, which I hope will clarify this. The one point that comes out of this is that when you have response, you get certain quantum pathways that contribute to it. And when you do it with entangled photons, you can actually suppress some of them or highlight some of them. So that gives you other degrees of control that are not available when you are doing it with classical fields. Now, before going into the story, I would like to give you some good news for those of you who lose sleep in October waiting for the phone call from Stockholm. There was a study of the longevity of scientists who got the Nobel Prize compared to those who were nominated. And it turns out that as a chemist, it buys you like 2 years extra life. And as a physicist, it's only like 1 year. This is the curve of the survival function of scientists with and who were nominated versus those who were awarded the prize. So the key number here is this, that for chemists is 2.35 years, and for physicists is 1.35. And there is a whole analysis in this paper, what is the reason for that. All right, so when we do nonlinear response, we do it with classical fields. We come up with a sequence of pulses, we control the delays, and we can get nonlinear response as a function of these various delays. And in NMR, people have perfected this to perfection. We heard a very nice talk by Daniel Idar, who were implementing methods of control to NMR, and it can be done also in the visible with optical response. And this is the nonlinear response function that I was talking about that depends on n times, and you get this information from the interaction with the classical field. And if you describe this in Liouville space, you can have this diagram that represents the evolution of the density matrix, and this is the ket, this is the bra, and you can describe everything in terms of what is the state of the system in each period. All right. Now, let's say that we want to do the experiment with quantum fields, and in particular, I will choose to do it with entangled photons. And these are photons that are created, say, by parametric down conversion, and they can be entangled in their polarization or in other degrees of freedom. Let's say in their polarization there is a vertical versus horizontal, and the two photons can be entangled. And let's say that I use this as a source to do my nonlinear spectroscopy. So the question is, how should I describe it, and what can I get from it, which is besides what I get from the nonlinear response function. So this is the wave function of the entangled photons. I have mode 1 and I have mode 2. It's a product and it is a proposition of such products. So the two modes are entangled. So I would like to calculate the response of the system to these entangled photons. So there are different schemes of entanglement. I will not go into that. And several years ago, several groups, in particular the group in Boston of Tarek and Saleh, predicted that if you do pump probe spectroscopy, the signal will scale linearly with the pump intensity rather than quadratically. And that will be the signature. And the idea is that the two photons act like one entity. You don't need to wait till at randomly another photon arrives. They come in pairs, and so the signal appears as though it's a linear spectrum. So their derivation was phenomenological, and we wanted to see how you can derive this rigorously and how you can learn more about the system by this. So basically, the signal goes like, as I said, linear. It's also inversely proportional to the correlation time of the two photons, the entanglement time, and to the area. If you put them in a small area, it will be better. Okay. All right. So let me take an example of pump probe spectrum. And now we found it useful to look at it in Hilbert space rather than in Loomis space. And now we are coming back to this forward-backward story, but in a different way. And in these diagrams, this is the evolution of the wave function. So I start here and I end up here. In Loomis space, I will go forward with both the bra and the cat. Here I go forward with the cat and backward with the bra. And these are the pathway that represents the pump probe spectrum. I'm looking at two photon resonances. So I have my three-level system. It has G, E, and F states. So I'm looking at, no, I'm not looking at Raman transitions, only at transitions that involve the state F. So I can have two types of groups. I call them pump modulated probe or two photon absorption. So here I start with G and I end up with F, GG to FF. This is what you call two photon absorption. Here I start with G and I end up in E. And in this case, since there are chemists in the audience, the pump acts as a catalyst. At the end of the process, I absorb and emit a photon from the pump, but the pump didn't change, only the probe changed. Nevertheless, it changed the absorption of the probe. In two photon absorption, both of them gets absorbed. So these are the two pathways, and then here the last one is the probe, K2, here the last one is K1, so I need to sum over both of them. Now, my point is, when you look at Loomis space, you think about this, that you are going forward, so you start in G and you end up in F, or here you start in G and you end up in E. When you do it with the forward-backward, you always start with G and end up in G, and it turns out that this has some very big advantages when we are talking with the entangled photons, as I will see. All right, so here is the formula for the signal, and it's given by integrals involving a 4-point correlation function of the material times a 4-point correlation function of the field. And you need to go along the loop and to proceed along the loop. So I first of all interact with the probe at time t4, then I go t2, t3, and t1. t4, t2, t3, t1. So all of these are ordered along the loop, and the point is that the field and the photons are entangled, so I cannot factorize it. The whole thing I cannot factorize into something of the material times something of the field. They are entangled. In each pathway, in each one of these pathways, there is a different function of the material and a different function of the field. Now, what will happen if the field were to be classical? If the field were to be classical, then this correlation function of the field will factorize. It will become a product of amplitudes. And then I can take it out of the integration, and then I get my response function. So the response function is the sum of these four pathways, and then it's multiplied by the field. But when there are entangled photons, I cannot think about this as a response function, because each pathway has its own counterpart function of the field. The 2 degrees of freedom are entangled. And one way to look at it is that these different pathways, when you combine them in different ways, give you information about spontaneous fluctuations in the system. Only the particular combination that you add them as they are gives you the response function. And it is non-causal. It is non-causal, which means you don't know who came first, whether the system or the field. Okay, so, I'm going back. See, I'm also moving here in little space, right? Okay, so now we define these transition amplitudes from the state G to the state F, and I have different transition amplitudes, and then I can take these signals and recast them in terms of these transition amplitudes, and I get the following expression. There is a little typo here. This formula is an absolute square of an amplitude. These are the pathways that correspond to two-photon absorption. This expression is not an absolute square of an amplitude. It's just an amplitude square, not absolute square. But there is an imaginary part in front. So the two-photon absorption pathways can be thought of like amplitude absolute square. The ones where the pump acts as a catalyst, you cannot think of them like this. Now, let's say that the intermediate state is off-resonant. I can take all of these are real, and I get amplitude square times a delta function, which is what you expect when the field was classical. But because of the fact that the photons are entangled, I will get contributions from both signals, from both terms. Okay, so now we put our entangled photon wave function into the story, and we can get this two-point correlation function of the field, which is this F function. This F function is a rectangular function controlled by the time t12. This is the entanglement time. It tells me that the two photons arrive within the entanglement time. So if I do that, the pump-up signal will be a product of my function of the material times these F functions, which are two-point correlation functions of the field, and then I will get my signal like, again, amplitude square and non-amplitude square, but it depends parametrically on the entanglement time of the photons. So I can plot the signal as a function of the entanglement time to get information. And here is what I see here. This is the signal plotted. I do a Fourier transform with respect to the entanglement time, T12. So this axis is this Fourier transform, and I get all kinds of groups of resonances corresponding to when this frequency is equal to omega EG minus omega E prime G, and so on. Now, the nice thing is that the states E in this model are off-resonant. Here is the pump. I'm going like this. The states E are all off-resonance. So with the classical fields, I will not see them in the spectrum. But because of the entanglement, I see resonances, and I can see these virtual states that otherwise will not show up. Now, what I can do next is, all right, now we can define different signals. I can define a symmetric signal because I can detect the two beams, so I can add the signal from the two beams. And I can also define a different signal. No, this is what I'm showing here. And I can also define the difference, and I define all kinds of combinations. All of them will show these various resonances. Now, let me take now another degree of freedom. I can add a delay between the two entangled pairs. So now the field has a delay, and one beam is delayed by tau with respect to the other one. And now I have interferences between the two pathways corresponding to absorption of one versus the absorption of two. And the signal will now depend on T and tau. It will depend on the entanglement time and also on the delay time. So if I calculate the signal, I can get now spectra as a function of the Fourier transform with respect to the delay time, and again it will show me these various resonances. Now I can also combine the two. I can do like a two-dimensional spectrum where here this axis will be the Fourier transform to tau, and this will be the Fourier transform with respect to t. Now, there is now a large activity on doing two-dimensional spectroscopy, where you take these multiple pulses with classical fields, and you vary the different delays, and you do double Fourier transform with respect to two delays. Now, this is a new type of two-dimensional spectroscopy, where the wave function of the photons is controlled by two parameters. In this case, it's tau and t. And I do a double Fourier transform with respect to those two parameters, and I get a completely different picture. So this remains to be explored. The only observation that was done so far is that the signal is going linearly with the intensity rather than quadratically. But nobody has explored this type of possibilities for obtaining nonlinear spectroscopy. Now, the nice thing is that you can vary these delays with a very high fidelity of sub-femtoseconds. So you can really get a very high resolution or very broad bandwidth, which is not possible otherwise.
Is it related to the other earlier traditional 2D spectra? Or
No, it's complete. Well, it's related in the sense that you are both looking at the same beast. You are looking at the material, but it's completely different set of parameters. So you are looking at it from a completely different viewpoint.
So the two times in where you're doing it now, but they're still related to the time difference between the pump probe, even though they're coherent with each other.
Not really. I don't know how to make it. I have a wave function of two entangled photons. This wave function depends on the entanglement time, which tells me how close the two photons come in pair, and it also depends on some relative delay. Now, this is not related to actual delay between two pulses. No, it's not. Yeah, it's a different set of parameters. So it will be nice to see. This is like a new direction that can be explored, and it could lead to many things. The important thing from a fundamental viewpoint is that here we are looking at spontaneous fluctuations of the dipole as opposed to looking only on the response. So it's something that cannot be accessed by nonlinear, although it's the same quantities, but one combination of them gives you the response, but the individual ones contain more information, so you can get a handle on the individual ones. So it's a different degree of control that needs to be explored. So just to answer your question, you could think about some of this if you created like two beams, two classical beams, which have a rectangular shape, and then you could think about the capital T in terms of their the widths, and you introduce some delay. So you have capital tau is much smaller than T. So you have two rectangular pulses, and you delay them by a little bit to create a phase. And then in this particular example, we could get a signal that looks very similar to what I showed you before, except that in this case it will go like the intensity square. It will not go like the intensity because it's classical fields. So you could mimic some of this with some control parameters of the pulses, but that's not generally true. All right. Let me now move to another story. I would like to show you another degree of control. You can create entangled photons in different ways, and one way is after they came out of the parametric downward conversion to pass them through a Mach-Zehnder interferometer, and this really couples the two photons in some different way and creates a different type of entangled state. And we have calculated again two photon absorption using these entangled photons. But now in the previous example, I looked only on two photon resonances. Now I'm looking at the whole story. So I can have two photon resonances involving the state F, but I can also have Raman resonances where I go from G back to G. So I have two groups of pulses. Here I see, and now it's very useful to look in the loop. So I go up, up, down, down, up, up, down, down. And here I go up, down in all the terms. So these are like two photon terms, and these are like Raman terms. Now in terms of the correlation function of the field, if the field were classical, all of them would give me E1 square, E2 square. However, if the field is quantum, what happens is that the terms that have up, up, or down, down, up, up, will have a term scaling like the intensity and another term like the intensity square. The term like down, up will only have intensity square. Which means if I take the intensity to be low enough, I can selectively look at group A, because group B will be higher order and I can neglect it. So in other words, the Raman type of terms will scale with the intensity square, but the two photon absorption terms will scale like the intensity. The intensity is small enough. So I can discriminate in this way. So let's see what happens. So this is the contribution of the group, or this is a three-level system, and I'm looking at the two photon absorption terms, and this is and I'm looking at a situation in which this transition and this transition are overlapping. So both pathways overlap. So this is the two photon absorption terms, and this is the terms that are Raman type terms. And then if you do the spectrum with classical fields, they are both on top of each other and you cannot discriminate. But if you do it with the entangled field, you could selectively do that. So this is one term. This is what you will obtain when you have it with a quantum field. This is the total signal that you will do it with a classical field. It's the sum of this plus this. And by doing the entangled photons, you discriminate the Raman and you can look selectively on this one. So this is another example where you can use this selectivity in order to choose a group of pathways. All right. Let me now come back to this issue of is it useful to think about this in Liouville space or in Hilbert space? All of these formulas would be much more complicated if I were to do them in Liouville space. In Hilbert space, they come very nicely. They give you these correlations. So as you know, we can do super-operator algebra where we can act from the left and from the right in order when we do in Liouville space, and then we can do the plus-minus operators that act symmetrically or antisymmetrically. And if you formulate the problem in this way, using this type of super-operators, you can get, in general, the signal looks like an integral involving such a super-operator green function of the material times the super-operator green function of the field, and you can do it either in the plus-minus or in the left-right representation, either way. And what happens is the following: that if you do the linear response depends on plus-minus, which means one is a commutator and the other is a detection. So this is the linear response function. It looks like a plus-minus type. When the field is classical, it has only plus-plus, because once you have a minus, it gives you zero. So you have only plus-plus times plus-minus, and this is the ordinary response function. But now, if you, I want to see, right, so this is the type plus-minus. So in general, what we have is, when you have one plus and the rest are minuses, this is the ordinary response function. When you have all of them pluses, it's pure fluctuations. And when you have a mixture, it gives you how fluctuations respond non-linearly to some perturbations. And all of these family of quantities are accessible if you do the spectroscopy with the entangled photons. So, for example, if you look at parametric down conversion is a combination of plus minus minus and plus plus minus. Now, most people, if you ask them what is parametric down conversion, they will say this is a chi2, because in a chi2 you put two fields in and you get a third field out. Here you just change the role, so they will tell you that it's a plus minus minus. However, since you have two quantum fields and one classical field, you have more fluctuations entering, and actually it's not correct to say that parametric down conversion is given by chi2, because there is also a plus plus minus contribution that is not part of the chi2, and it contributes to the parametric down conversion. And let me give you another issue where, you can see how the Hilbert space picture looks nicely. Let's say that I look at a signal generated at minus k1 plus k2 plus k3. And now, if I were to formulate the problem in Liouville space, you will get this type of diagrams. There are three terms. Now, minus k1 means that the k1x to the left, and plus k2 plus k3 means that they are acting to the right. And if you add these three signals, you will get your signal. Now, this is very nice. This is a description of the photon echo. But let me show you some discrepancies here that are not clear. This signal, the signal frequency is always equal to minus omega 1 plus omega 2 plus omega 3, which means that this is a kind of parametric process where the initial state and the final state of the matter has to be the same. If you look at it in a loop, I go from G to G and you can understand that. But if you look in the Liouville space, the final state can be different state of the matter. So you don't see why it is a parametric process. Also, when you look at the arrow, this arrow represents absorption because I go like this. And in this diagram, this arrow X from the right, it represents emission. So is photon 2 absorbed or emitted in this process? The signal is the sum of all three, and you will expect that only one process occurs. When you look at it in Liouville space, you think that this is absorption and this is emission, and they both contribute to the same process. However, when I do it in Hilbert space, I go in a loop, and when I go here, I go backward in time. So this is absorption, this is also absorption. Because it's emission when I go forward, but it's absorption when I go backward in time. So when you think about this in this loop, you can think about the process in a somewhat more intuitive manner. However, you have to give up the convenience of working in real time and moving forward in time. So I always thought that going backward in time is something that should be avoided because it's not intuitive and not physical, but for many observations it could give you actually a nice insight, especially if you have frequency domain techniques. Right, so this is just a summary that in Liouville space we work in physical time and we can go only forward, but once I formulate everything in the loop, then the problem, all these problems are cured. So to summarize, I showed you several examples where, first of all, you have a formalism in which you can treat two interacting systems and develop something analogous to the response functions, but these response functions will not be causal and will give you different information about the system. And then you could see how you can think about the same piece in Liouville space or in Hilbert space, and you can choose it to your convenience. Thank you.
Yeah, when you have two photons that are overlapping in time and they're in superposition, it feels like it's just one photon that has been shaped in a fancy way.
Yes.
Is that true? And any comments on that? So it's just a nice way to look at a specific type of shaping.
Yeah, you can think about it in a certain way, but it's deeper than that because you can do shaping of a classical field. Okay, and here there are, if you do a shaping of a classical field, the signal will still be given by ordinary response functions with some time integrals. But in this case, it's given by other type of response functions. So in some way, yes, in some way, no. And it would be nice to explore the connection between the pulse shaping and the entanglement. There is some connection, but it's not the same.
I'm having some trouble understanding. Your classical field, a classical electromagnetic field has a well-defined phase, but undefined number of photons.
Yes.
Now, your entangled photon states, I presume they're well-defined photon numbers, but their phase is not well-defined. Am I correct?
Well, you can have different schemes of entanglement. You can have entanglement only by polarization, for example,
Okay.
what is called type 2, and then there is no problem. You can do entanglement in Fock space, and then you will not have the phase. So there are, yeah.
So your entangled states do have exact phase.
We use type 2, which means they are
Okay.
entangled by the polarization. Yes.
Thank you.
At the beginning of the week, you mentioned something about
in your talk you would actually have a generalization of a kind of a relationship between response and fluctuations, and I saw certain components of that. But is there some kind of theorem here, which is a generalization of a fluctuation dissipation theorem?
Okay. This is a very deep issue, and I would say that there is no such simple theorem, and let me explain why I think so. When you do linear response, you have you can have two functions that are independent. You can have v plus t1, v plus of t2, and then you can have a v plus of t1, v minus of t2. This quantity is the response function, because the minus time must be earlier. If it's at the end, it gives you 0. So this quantity is causal, and it's the response function. And this function represents fluctuations. And then by simple tricks, you can show that the Fourier transform of this and the Fourier transform of this are related, and this is called the fluctuation dissipation theorem. Okay? So in linear response, there is no problem. What happens if I have nonlinear response? Okay? The response is minus, 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 and plus. So the response is a very specific combination where everybody is minus and the one is a plus. But now, if you start playing with the pluses and the minuses, you have many more combinations. 2 pluses, 3 pluses, 4 pluses. So there is no way that this one quantity will carry the same information as all the other ones. In the linear response, it's a special case. There is one quantity for fluctuations and one quantity for response, and they are related. And in this case, you have a broad family of quantities that represents different type of fluctuations. So there is no unique relation between response and fluctuations. Fluctuations contain more information. You can derive certain like partial relations on some quantities and so on, but there is nothing strong and general. And in a way, you can look at it in a negative way, but it's also a positive way. It tells you that there is more information that you can learn by exploring these other quantities.
So to perhaps promote a couple of questions. So everything we've heard, I think, so far from the control side of the people in the audience, right, has all been classical fields.
Classical, yes.
Do you expect to be able to control things in different ways?
Well, absolutely, because when you create this, you have a new set of parameters that you can use them as control parameters. In this case, these are the parameters of the wave function of the entangled photons. So in principle, I cannot do it, but some experimentalists can do it. They can control this, and I showed you two-dimensional spectrum, and I'm sure this can be controlled and manipulated. Yes?
Maybe on the experimental side, what are the times that can be experimentally achieved? Tau and T, for example, in your first case?
Tau can be controlled to within even less than a femtosecond, because you control it by a delay line, and it's very good. You know, T also, T there is a very broad range of times. It can go to picosecond or even longer. Yes.
So just to come back to whether this question of control. So what I understand about this is that when you have two photons that essentially came from the same parent that recombine, then they behave as if it's a coherent two-photon process. Otherwise, two photons behave as if it's an incoherent process.
Okay.
So
but the signal will be dominated by the ones that the two came from the same pair, because this will be much more favorable. And this is why it scales linearly. Because if you were one photon from one pair and another from another pair that came at random, the signal will scale quadratically. Okay? So you can discriminate in this way because by the intended.
And it also, I mean, it gives you a much narrower time window. You can say, I mean, what I know the Zilberberg group has shown that even with even with pulses of a longer duration, that you essentially have a very short, you can have effectively a very short correlation time.
Absolutely.
Because,
It's like doing shaped pulses with a very broad bandwidth, because you have a control over a very short time, and effectively, but it enters in somewhat different way. Yes, you're absolutely right.
So now overall, I guess it's not clear to me if this actually gives you, in a way, more control or less control. I mean,
It gives you different control.
it gives you different control.
Because it enters, it's not, there is no one-to-one, like Fourier transform relation between controlling the pulses and the wave. It's a different thing. Basically, you are having these different contributions, and each one of them will have its own field factor. It's a different control that you cannot get with any classical field.
So what do you have control over exactly? Just restate it. What can you control?
You control, if you have a 4-point correlation function of the material times a 4-point correlation function of the field. And the signal is a sum of 4 such terms. Now, since each term has its own correlation function of the field, you can discriminate between different correlation functions of the material. In the classical field, all the correlation functions of the field are the same. So they drop out, and you get a quantity that is a purely material property. This is the response function, and this is what everybody is doing when you do a classical field. And otherwise, you can see separately the different contributions.
This is a naive question to the control people. Is it easy to build in the entangled states into the methodologies that you have to control?
Well, I assume so. It's just another parameter. Just, you know.
A different approach. I think you would model, I think, if you want to do it properly, you model the entire system quantum mechanically.
Exactly.
You really have to model it as a system and the quantum controller. So you can't...
No, but that's what it does. You treat it, but then it factorizes into a function of one system times another function of another system.
But I think you would have to do it, I mean, you have to be careful with the modeling. I think you would want to model it differently. You want to model the entire system quantum mechanically. At some stage, maybe it simplifies, but you...
Well, the way I wrote it, you have a correlation function of the field. You know it analytically, so it's function of parameters. So now you do the control on that function.
I see. So, what
So instead of controlling the field, you control the correlation function of the
But
field.
once you have reduced it to that, you could probably use just the usual algorithms to try and find the optimal parameters to give you, I don't know, some kind of optimal correlation for
Right.
because of discrimination. At that
Right.
stage, you could do it. But
Right.
generally, I think you would want to treat it, you would need to be careful with treat it. Now, I have one question, which I don't know how to explain it. So you were talking about these parametric down conversion processes to generate entangled photons. There's some other schemes that also generate entangled photons, but they are different. So, for instance, they may generate polarization entangled photons, but there's a time delay.
Yes.
And would that give you the same? So if you had, for instance, so the photons are like, if the first photon is horizontally polarized, and the next photon that will come in, it's also horizontally polarized, and you can have as many as you want, but it's always a time delay. Would that change your analysis, or is it important that they are coincident, basically?
No. Basically, it will all translate into different models of this 4-point correlation function of the field.
What if you had an n-photon entangled state? Because there's some proposals to generate this n-photon entangled state, but they're different from null states. So for some application you need null states, that means they have to be like coincident, and in those other schemes the photons coming sequentially, but they're entangled. So would that kind of sequential, like if you have a sequence of entangled photons, would that work for your schema? Do you expect to be able to do even more if you have, say, a 10-photon entangled state, if you could control?
Well, the formalism allows you, then you will need a 10-point correlation function of the field. Okay, because that,
But
the
would you
way,
expect to gain something from that, or will there be like, is it maybe a law of diminishing returns? Because if you have like 100-photon entangled state, and then would you gain
Okay.
more information?
let me tell you why I think that you will gain definitely. Let's go back to the classical fields, When you do multi-dimensional spectroscopy, you can have 2 dimensions, 3 dimensions, and so on. And you know that as you go higher, you gain more information that cannot be obtained by the lower ones. This is another type of family of multi-dimensions, because when you have 10 photons, you can control 10 delays and so on. It's a multi-dimensional. For sure, it contains more
So the
information.
more photons you have potentially, and the more control you have over the entanglement, potentially that would really
You have,
allow you to do interesting stuff.
it allows you to get information that cannot be obtained otherwise. Yes, absolutely.
Very interesting.
That's a general, yeah.
Well, there, in a lot of the papers of an ultra-fast salvation response and so forth, there's a whole...
Salvation or salvation?
Salvation.
It's not lunchtime. We got another talk.
There's a whole question of whether or not signals coming from exciting state or ground state response and so forth. And so I imagine that those would correspond to different pathways in the Liu belt.
Absolutely.
And then if you can distinguish those now using this, so maybe this would be actually very useful for distinguishing excited versus ground state response.
If one could design, potentially, yeah, that's the type of question that in principle you can ask. If you could design, you know, a file sequence that will do that, yes, yes, yes.
On that point, on a practical point, experimentally, it's easy to shape these classical pulses. Is it also experimentally easy to control T12 and tau in the experiments, so that
Yeah,
you can actually have an algorithm
Yes.
like they have at the moment with the shape?
You know, people like Aaron Zilberberg in the Weizmann Institute have been doing very nice work on getting intense pulses of entangled fields and shaping them. Yes, yes. So it is possible.
Okay.
It's a naive question. How many photons now people can read entangled? 5, 6?
I don't know what's the record. You know, few. I mean, I don't know. You know, I don't know exactly the record, but it's few. It's not.
Less than 10.
I would say.
Less than 10.
I think the record is 8. Could be tomorrow somebody will come up with a paper that is 10.
Okay. Let's thank Shaul for a great presentation. Okay, last talk for the session is from Sonia Sherman, and it's Hamiltonian and Markovian reservoir engineering for quantum systems.
So if my computer is probably going to sleep.